Big data is difficult to classify. A classification problem is where we have two or more categories, and we have something that's uncategorized, and we want to figure out which category it's in. We tend to number the categories 0, 1, 2, things like that. Here's a simple classification problem. You've got a regular polygon. You want to predict if it's a triangle, class 1, or not a triangle, which we'll call class 0. This is actually a pretty easy task. Here's the data. Notice that you can just look at the number of vertices and figure out, for instance, that this observation is of a polygon that is class 1, a triangle. Whereas this is an observation of a polygon that is definitely not a triangle. If you only have 2 or 3 variables, then we can actually visualize as points with the class number. And we're going to be looking a lot at linearly separable. Linearly separable means, in 2 dimensions, we can separate with a straight line. How would we predict the class of an unlabeled observation? Quite simply, if it's linearly separable, as this set is, then we can just predict the unlabeled observation is in the same class as its nearest neighbor. And this is what's known as a nearest neighbor classifier. It's the simplest classifier that you could imagine. But we only want to consider linearly separable data. Some data sets are clearly separable, but not linearly. However, we may be able to transform to linearly separable, for instance with log-log space. Or we might be able to define new variables that allow us to separate polynomial data, for instance. Here we let y be x squared, z equals x plus y is a plane. In 3 dimensions, the x, y, z space, we have something that in 2 dimensions is not linearly separable. In 3 dimensions, it clearly is linearly, i.e. separated by a plane. If we can transform and get linearly separable, then that'll be okay in this class. But anything other than linearly separable is not okay. Arbitrary curves produce arbitrary predictions. Here we have data, and we're going to arbitrarily separate the zeros from the ones. Class 0, as you can see, we're making it so that all the class zeros are on one side of this curve, and all of class 1 is on the other side. Now, let's suppose that we do it again. Separate zeros from ones. Again, these are points labeled with the 0, and we separate them with a curve from class 1. Now suppose we have an unlabeled observation. Using our first curve, it's clearly class 1. Using our second curve, it's obviously class 0. This is arbitrary. This isn't going to give us good predictions. Instead, we use dimensionality. Data that can't be separated in 2 dimensions may be separable in 3 or more. And in general, we have m-dimensional data. Perhaps it's linearly separable in greater than m dimensions. For example, XOR data is not linearly separable in 2 dimensions. The x and y is separable. The x or y is separable. But XOR labels the 1, 1 and 0, 0 points the same, therefore it's not separable. However, the XOR is linearly separable in 3 dimensions. So to see this, let's suppose that we rename the 1 and 0 classes as the false and true classes. This gives us the actual XOR. So 1 XOR 1 is false. In the z-plane, we're going to put z equals absolute x minus y, and that additional variable is going to give us a 3-dimensional space. Clearly, the XOR is linearly separable in 3 dimensions. Data that can't be separated in 2D may be separable in 3D. Here we see a large collection of data, and here is the XY projection of that data with the labels. But in 3 dimensions, clearly it's separable and linearly separable. And from now on, when we say separable, we'll mean linearly separable. Let's look at a real-world example. This is from 1936, Sir Ronald Fisher looked at the iris dataset, which has 4 features: sepal length, sepal width, petal length, and petal width. You can see some of those there. We're going to say class 0 is I-setosa, class 1 is not I-setosa. Sepal and petal length linearly separate I-setosa from not I-setosa. Sepal length and sepal width is not separable. However, sepal length, petal length, sepal width is separable in 3 dimensions. Let's relabel the data with all 3 classes. We have 0s, 1s, and 2s. The 0s are separated from the 1s and 2s, but there's no way to separate the 1s and 2s from each other. I-setosa can be linearly separated from the other 2, but the other 2 cannot be linearly separated from each other. If we go to 10 to the 50th, we can separate there. However, there's a huge problem. The iris data doesn't have 10 to the 50th data points. So even though we can definitely separate, it'll be an example of what's called overfitting, an arbitrary prediction because linear separation was in a space that was too large. So if we have complex data, we're not going to get linear separation in low-dimensional contexts, and we might get overfitting in high-dimensional contexts. For example, let's look at this set of microarray data again. We have labeled 1s and 0s. The 1s are those things that were produced experimentally, and the 0s are genes that are not. It's not linearly separable. What does this say about big data? That it's often only linearly separable in very high-dimensional spaces, and often very, very, very high-dimensional spaces. But that can be a problem itself, in particular overfitting.